This is the first section of Chapter 8, Scheduling, and in this section we're just going to talk about some basic elements and some basic vocab before we get into the real math of it all. The ultimate goal in this chapter is to schedule events or tasks in a certain order so that they can be done efficiently. So this little acronym here, CPM, that stands for the Critical Path Method, and we're going to be developing that throughout this chapter. So scheduling goes into a lot of different areas, whether you're planning to build a space station, that takes a lot of work, whether you're just building a house. If you've planned a wedding before, you know there's a lot of things that have to occur before the next step can occur. So we're going to have to take that into account. And even something like arranging a basketball game. Alright, so like you can't start the game until you know the floor is clean or until you know you have referees scheduled to come officiate the game. So again, it's not about just getting all the things lined up that you need to have. It's about putting them in the right order. Our first vocab term is the processors. So any job is going to require workers who carry out the work. So we're going to refer to the processors with the variable n. So, and this should say where n is greater than or equal to 2. Okay, if you just have one person working, there's no sense in really having to do a complex schedule if they're just doing all the tasks. So in this chapter, we're usually going to have at least 2 workers doing a job, sometimes 3, maybe 4, but it should always be at least 2 to do any of these problems. And we'll just denote those processors as P1 for the first worker, P2 second worker, so on. Our next term, task. Any project that's completed, we usually have jobs or tasks to be completed. And within this chapter, we're going to define a task as an indivisible unit of work that cannot be broken up into smaller units. Okay, so say there's 2 mechanics working on a car. There's one mechanic doing the exterior paint job. We're going to assume that they can't split that work up, that is only designated to one of the workers. And then each of these problems, we're just going to label the tasks with capital letters. So generically, we would just use A, B, C, and so forth. And to add to that, at any particular moment in time, a task can be one of 4 things, one of 4 states. So it can be completed, so already done. It can be in execution, so currently being worked on. It can be ready, which means we haven't started it yet, but it can be started, and ineligible, which means not able to be started yet because something else needs to be completed before we can get to that task. The processing times are the time it takes to complete a certain task, and we're going to assume without interruption. And we'll just denote that with the capital letter and the number beside it. So for example, task X takes 5 hours, minutes, days, whatever you're working with in the problem to complete that certain task. Precedence relations are going to be really important in this chapter. These are just restrictions on the order in which the tasks can be executed. So for example, in school, can't go on to take English 2 if you haven't completed English 1, or if you want to go on to take calculus, you would need to complete pre-calculus before doing that. I can apply that in almost any situation. If I were maybe needing to tune up new guitar strings, well, I can't tune the new strings unless I've taken the old strings off. Then we got to put the new strings on, and then you can't do the tuning until each string is on. So these are just a way to kind of keep us in check that we're doing things in the right order, so nothing gets messed up along the way. We can represent a precedence relation with graphs. So for example, if task X needs to be completed before task Y, we can represent that, and that you see is in graph A. So Y is dependent of X, so that's what's going on right here. X needs to be completed before we can go to task Y. So next, if you look at graph B, we just have two isolated vertices, tasks X and Y. They have no precedence requirements between them, so we're going to call those independent. Looking over at graph C, we have a relationship that is transitive. So we need to complete task X before we can complete task Y, and we need to complete Y before we can complete Z. So therefore, XZ is also a relationship. X needs to be completed, of course, before Z can be completed. And lastly, we should never have a cycle going on in this chapter. So if I start with task X, and then I need to complete X before Y, and then Y before I can do Z, and Z before I can do W, and then W before I can do X, that doesn't really make any sense. Okay, this should be in a very strict, straightforward order. So no cycles. Now, I hope this never happens to you, but imagine this. Imagine that you've wrecked your car, and you get out fine, but you need to take your car in to get some maintenance. So above, we have a picture of some scheduling charts where we have 4 tasks. So task A, task B, task C, and task D that needs to be done on the car, and there are currently 2 workers available to do those tasks. The specific tasks that need to be done, so those 4 tasks: A, the exterior body work; B, the engine repairs; C, the painting and exterior finish work; and D, we have to repair the transmission. And notice down here on the bottom, this is important. So the only precedence relation is AC, which means the exterior body work, okay, needs to be done before we can move on to C, the painting and exterior finish, which should make sense. If there's a fender bender or there's some bumps in the exterior of the car, we should probably fix that before we try to paint on it. And if you look in the chart, this does follow that rule. We have A ending here at 4 hours, and after that 5th hour, C gets started. So again, this chart follows that precedence relation. Now, while this chart does follow the precedence relation appropriately, it is efficient. Notice we have processor 1 doing the smaller tasks and processor 2 doing the tasks that take more time. And then in the end, we have all this idle time where processor 1 is not doing anything. So the goal is to sort the tasks around while obeying the precedence relations and minimizing the amount of time that the complete project takes. This particular setup takes 12 hours to complete, so we would just denote that saying fin equals 12 hours. So we're on the same problem, but we've changed up the schedule a little bit here. So this looks a little better. We only have 1 hour of idle time, and the project gets done 10 hours instead of 12. However, the precedence relation was not obeyed. Now, A needs to be completed before C, and here that did not happen. A was completed 4 hours in, and C was started 3 hours in, and we cannot do that. Now, if we adjust things just a little bit, and we make processor 2 just take an hour break and move task C over just a tad, A is finished at 4 hours, and then right as task A is completed by processor 1, processor 2 can pick up from there and start task C. And that's going to give us 11 hours, which is a pretty good schedule, not a ton of idle time, and we have obeyed the precedence relations. And we'll denote that with fin equals 11 hours. So you may wonder, can we do even better than that? Well, no. The problem is if A takes 4 hours and C takes 7 hours, and you have to do A before you do C, 11 is the minimum amount of time that we can finish this task in. So we're going to call this the optimal schedule. It's the best schedule so far, and the 11 hours is the optimal finishing time. And just to be really nitpicky here, we're going to use OPT, so opt, instead of fin when we're referring to the finishing time, which is the optimal time. So we'll say opt equals 11 hours. The last thing to be discussed here is the minimum time for a project to be completed. So in this particular example, task A, B, C, and D add up to 19 hours of task time. So we're going to take that total processing time and divide it by n, the number of processors, so it'll be 19 divided by 2, and we'll get 9.5. Now, when we did the problem, we saw that the best we could do is 11, so it's important to know when you're doing this, yeah, it's a good idea, it gives us a good idea of the minimum amount of time required, but that doesn't mean we're going to be able to do it in that time. So we know for sure that we could not finish the project in less than 9.5 hours, but chances are we're not even going to be able to do it that soon. It may require a little more time than that. And to add on to that, adding in processors or workers can sometimes be efficient, but sometimes not. So you probably heard the expression too many cooks or too many people in the kitchen. So if there's too many people trying to do the same thing, it actually harms the process. So see, when we did 19 divided by 2, we got 9.5. Now in this particular example, we had those 3 hours of idle time, which isn't that bad. If we were to actually work out the problem again, we're not going to in this video, but if you had maybe 3 workers doing the tasks, that's a minimum of 6 hours, or 6 1/3 hours, but we could potentially be seeing 14 hours of idle time. If we add another processor right here, 19 divided by 4, that gives us a minimum time of 4, almost 5 hours, but we've got a lot more idle time because there's not as many tasks to be given out to each person. So in the end, to reiterate what was said a slide or two ago, we could, with like these 2 processors, get it down to 9.5 hours, but because of a precedence relation, the best we can do is 11 hours. So that's always going to be one of the most important things to look at when starting any one of these problems.